Alright, let's have a look at the first video. We're looking at the first example. We're looking here at Newton's oops, second law. I'm not going to go through the first and third law that you can do on your own time because it's mostly theory. But for me, what's important is Newton's second law. It has a lot of calculations, so I'd like to get through that with you. Right, let's have a look here. It says I have a force of 300 newtons acts downwards on a 30 kilogram block at 40 degrees to the horizontal, as shown in the diagram below. The block accelerates to the right along a rough horizontal surface. Now let's just dissect that situation. So I've got a force that's going to be 300 newtons, and my mass of my block is 30 kilograms. My value for theta is 40 degrees. I know that there's an acceleration. It's a positive acceleration because I'm going to say anything that moves to the right is positive. So I'm going to say acceleration is positive if the movement is in that direction. And then it says there is a rough surface, so the force of friction is greater than 0 newtons. Alright, so once I've got all of that sorted out, let's have a look here. Question 18.1 says calculate the magnitude and direction of the component of the 300 Newton force that accelerates the block horizontally. So if my force was here, you see where this dotted line is? If my force was there, then I could use this value, this 300 newtons, right? Oops. I could use the 300 newtons, but I can't because I have a situation where I have a little bit of an angle, and because of this angle I need to sort out my information. So what's happening at this point? Let's say I have my little my object there. What's happening is this object is being pushed across the surface, right? So when I'm looking at it, I know that I have a force that is coming down like this, and this force is here, is worth 300 newtons. Right, at the exact same time, I have other forces that are also contributing. This object, I notice, is on a surface. And if an object is on a surface, then I know that I'm going to have a downward force there of mg. I also know if it's on the surface, I must have my normal force. Oops, undo that. Fn. And at the exact same time, in the opposite direction, I have a force of friction that's doing something like that. Force of friction. All right, let's have a look at our information just a little bit. Right. Over here in this diagram, I know that this degrees are 40 degrees. But this angle, this little situation here, that is what we call a resultant force. Now, in your question, it says you need the components. Now, if my resultant force is doing this, I need its components. So I know there must be a downward component because the arrow is moving downwards, and there must be a component to the right. So it's got right here, and I got down here, and which makes this little thing my resultant force. Now what they're asking us for, they want to know what accelerates the block horizontally. So I'm just going to go into this diagram and I'm going to edit it. So basically I've got that sort of setup. And what you'll notice now, I've got a horizontal force there, and it's starting to make a shape. What kind of shape? A Z shape, which means that that angle over there is also 40 degrees. All right, now that I have that, I've got myself a triangle. Just going to draw it here. I've got a triangle, and it's doing this. And this is moving here in that direction. So I've got, it's moving to the right, it's moving down, and remember, if it is. All right, so I don't know any of this other information, so I need to first sort that out. So remember, if I want components, I can either say F is equal to, F res is equal to F cos theta, or F res is equal to F sine theta. All right, so in this situation, I'm looking now at my f of x. And if I'm looking at f of x, remember it's going to be the x components formula, which is cos theta. So for 18.1, it's going to say f of x is equal to f cos theta. Now the magnitude of the force I know is 300 newtons. Cos and the degrees that we're working with, we have a look here. I have 40 degrees. And that's going to give me 229.81 newtons to the right. So now I know that this value here is 300. I also know that this one is going to be 229.81 newtons. So I've got 2 bits of information there. Right, the next thing they want is the acceleration of the telling you if the acceleration of the block is 2 meters per second squared, calculate the magnitude of the frictional force acting on the block. Right. When we do a question like this, 18.2, the first thing you need to show your marker is you need to say anything that moves to the right would be considered as positive. And if we ask to work out acceleration, the formula we're using is F is equal to ma. Except F here means F net. So we need to sort out all of our forces before we start with this sort of thing. All right, let's have a look here. They want the frictional force. Right. What I know about F net here is that F net is equal to the forward forces minus all the backward forces. So at this point, if I wanted F net, then I have to use my forward force. So what's moving it to the right? What's moving it to the right is the 229.81. That's my forward force. Minus the backward force. But I don't know the backward force. So that's just friction. Alright, so now I can take this F net and pop it into my calculation. So therefore, F net is equal to MA, where F net is actually 229.81 minus, or rather, yeah, the force of friction. So we can even say, yeah, minus the force of friction times the mass, which I know is 30 kilograms, times the acceleration, which they gave you at 2. So M is equal to 30, A is equal to 2. We found out that Fx is equal to 229.81. Alright, so I'm going to move that over to the other side. And what I'm left with is a negative force of friction is equal to 30 times 2, which is 60, minus 229.81. And that's going to give me negative force of friction is equal to 169.81 newtons. Minus that, sorry. Minus cancels out. And force of friction is equal to 169.81 newtons to the left. Right, so I've got that sorted out. Right, 8.3. 8.3 says calculate the vertical force exerted by the block on the plane. Right, when I talk about vertical in this sort of situation, I need to look at actually how many downward forces do I have. So technically speaking, if I just use this other color, technically speaking over here, I've got down. So my Fy. And over here, I've also got down, which is my mg. But do I have anything that's going up? Only the force of the normal. Alright, so let's have a look here. 8.3. I know that Fy, the component, is F sine theta. Yes. And I'm going to get 300 times sine 40. And that's going to give me Fy is equal to, just pop that into your calculator, I'm going to get 192.84 newtons down. So in this situation, we're going to take down as positive because things naturally fall in a downward direction. Alright, so I've got that. That's the one. I've got two. Remember, I said I've got Fy that's going down, and I've also got W that's going down. So the other thing I've got is W is equal to mg. My mass of my object is 30 times gravitational acceleration at 9.8, and I end up with 294 newtons. Right, so that's how that looks. Right, the next step in this one is that now that I have my two forces which are moving in a downward direction, I'm going to say 𝐹net for down is equal to Fy plus W. My Fy is 192.84 plus W, my weight is 294. And that's going to give me 486.84 newtons downwards. That's my 𝐹net for that situation. So if I'm looking at 8.3, just do this. Oops. If I'm looking at 18.3, sorry, just fix that. 18.3. They want the force, the vertical force exerted by the block on the plane. So if I'm looking at that sort of situation, remember I've got an upward force and a downward force here, there. I've got the block on the plane and the plane on the block. So the force exerted by the block on the plane is upwards. But here, when I calculated downwards. But I know that Fn is equal to mg, or equal to the weight. So therefore, the force of the normal, is equal to 486.84 newtons upwards, which is also the force of the block on the plane. There we go. And that's how you get to the end of 18.3. So please make sure that when you're working through these questions, you actually have to take into consideration component forces. And that's how you would work on a question that has a push or pull force at an angle. then you're going to have to work with component forces and get your answers in that way. All right, let's have a look at the next one. All right, the next one says 2 crates, 3 kilograms and 5 kilograms respectively, are connected with a thin rope and are pulled up a rough plane, which has an incline of 30 degrees. So I'm just going to add information here. I'm going to add in 30 degrees there. To the horizontal, a force F is applied parallel to the plane as shown in the diagram, accelerating the system of crates at 2 meters per second up the slope. The frictional force acting on the 3 kilogram and the 5 kilogram creates 10 newtons and 17 newtons respectively. And then we have 3 questions that we need to answer. Let's have a look at that. If I read the first question, number 20.1, I need to draw a fully labeled free body diagram for each crate. So what I actually do is, before I even get into that, I do my own thing. I first have to decide what's happening here. Right, the first thing that I decide is there's an incline here. So I can't have forces that are going forward. I can't take any forward forces as what they are, or frictional forces as what they are. I need to look at what's actually happening. So remember, if something's on an incline, it cannot just have an mg value there. It must have components, an F component and a Y component, an X component and a Y component. So I know that this is going to be mg cos theta, and then this is going to be mg sine theta. All right, so let's look at this in a little bit more detail. All right, question 1, draw a fully labeled free body diagram for each crate. Right, 9 marks. So let's have a look here. We've got a 3 kilogram and we've got a 5 kilogram. So I'm gonna draw the 3 kilogram first. With the 3 kilogram, let's just look at all the forces that are acting on it. I know that because it's on an incline, I must have component forces. All right, so, and it's on an incline, so I know it's on a surface, so I gotta have the normal force on the top, and then I've got to have the force directly underneath it. So up here I have F normal, and down here I have mg cos theta. I know that naturally this block would love to slide down the slope, right? But in this situation, it says a force F is applied parallel to the plane, which means it accelerates the system. So the forward direction of motion is going up and the friction is going down. So up here, I'm going to have force applied. And down here at the bottom, I'm going to have force of friction, which is equal to, what did they say? 10 newtons. So when you see this word respectively, that's important, because here they gave me 2 masses and then it was followed by 2 forces. They're in the right order. So the 3 goes with the 10 and the 5 goes with the 17. So just make sure you remember that. So this force applied here is not any kind of force applied for this thing. It would be better for you to say for Ft, or it will be better for you to say tension. Right, that is what's happening like right now with the 3 kilogram. All right, the second thing that you have to draw, and you'll notice I didn't put the weight in, because remember what we the weight or the mg value, because this is we're drawing a free body diagram, a component diagram for the 5 kilogram. All right, so for the 5 kilogram, same situation, a little bit different. We know it's on a surface, so I'm definitely going to have a normal force, and straight underneath it I'm going to have my perpendicular force. So I've got force of the normal, and then over here I've got mg cos theta. Then with the 5 kilogram block, what's directly pulling it up is a force, and that force is accelerating it. So I've got that force applied. But also what's happening is, can you see this 3 kilogram block? What would this 3 kilogram block naturally want to do? It's going to want to move downwards. So for the 5 kilogram block, it's tagging along this 3 kilogram block, and this 3 kilogram block wants to go downwards. But at the same time of that 3 kilogram block pulling the 5 kilogram block down, there's also a rough surface. So on top of that force, I still have another force, which is over here, which is force of friction. So I need to make sure that I get that into my diagram as well. So here I've got force of tension, or I can say Ft, and I've also got an additional force of friction, and for this one it's 17 newtons. So for 9 marks, this is what you should be drawing. So break it down. You could draw them all at once, right? But it's better not to. So when we talk about, this here is the F applied, but because it's accelerating something, you can even call it F thrust. R-U-S-T, F thrust. So your thrust force it's accelerating it, and your tension is kind of pulling it down. So that's how you would do 20.1. Right, 20.2. It says you calculate the horizontal component of the weight for each grade parallel to the slope. So right at this point, if I'm looking at that type of force, they want to know naturally what's going to happen to each of these objects. So when we talk about a horizontal force, in these sorts of situations, we're looking at what's kind of like its natural way. So for the 3 kilogram block, we're looking at the weight in the x direction, which is going to be what's natural to it. So the 3 kilogram block, what's natural to it is down the slope. So I'm going to say Wx is equal to mg sine theta. The m is 3, the g is 9.8, sine, and then the theta value was 30 degrees. So once you pop that in to your calculator, you should get 14.7 newtons down the slope. That's what would have been natural, because here if you read the question, it's talking about the weight, right? And when we talk about the weight, we're talking about gravity and weight go together. All right, naturally for the 5 kilogram object, it will also want to go down the slope, and we do the same calculation. It's mg sine theta. So if you ever look here, can you see how this mg that I'm putting in is the weight? So I've got 5 times same thing, 9.8 sine 30 degrees, and you pop that into your calculator, and you're going to get 24.5 newtons down the slope. All right, so that's natural. That it's natural weight. That is what's going to happen to this sort of situation. All right, let's look at 20.3. Okay, with 20.3, it says calculate the magnitude of the applied force and the tension T in the rope. Right, so let's work with what we do have. Let's work with each block. Let's say I'm going to work with the 3 kilogram. That's at the bottom, so it's fine. I know that 𝐹net is equal to MA, right? I also know that for the 3 kilograms, there's different forces that are acting on this situation. The first force, I've got my forward force. So remember, 𝐹net is forward minus backward. My forward force in this whole situation is the tension minus the friction. Makes sense? Right. So now I've got, so this is 𝐹net. So 𝐹net, and I'm going to substitute it here. I'm going to go, 𝐹net is equal to T minus F, which is equal to MA. Now, I don't know tension, but I know that the frictional force for the 3 kilogram one was 10. So minus 10 is equal to the mass, which is 3, times the acceleration, which they gave it 2. So T minus 10 is equal to 6, which means that T is equal to 16 newtons. So now I've solved that situation because I'm looking at the object with the least amount of forces, which is the 3 kilogram. Then I'm going to look at the 5 kilogram. With the 5 kilogram, again, 𝐹net is equal to MA. And I know that 𝐹net is actually equal to forwards minus backwards. So my forward forces for the 5 kilogram is the forward force, the force applied, plus the tension. Oh no, whoops. So let's say plus minus the tension, plus minus friction. So that's what that looks like. So I'm just going to say F applied minus tension minus friction is equal to MA. So the force applied, I don't know. So F applied, I don't know. Minus the tension, which is minus 16, which we got from the previous question. Minus the friction of this one was, I think, 17. Minus 17 is equal to the mass, which is 5 times 2. So minus 16 minus 17, I'm going to get negative, I think it's 33, is equal to 5 times 2, which is 10, and that's F applied. This is going to move to the other side, and the F applied is then equal to 43 newtons. So now I've answered my 2 questions. This you can do on the side, just as background, or you can actually do the calculation. I could have went here and done F applied is equal to, minus 16 minus 17, and I would have gotten that 𝐹net is actually F applied minus 33, and then put that value in for 𝐹net. So I could have jumped from there all the way to there somewhere in this, this one here. So you could do it by itself, or you can just bring it into the equation. It's up to you how you're going to do that. But that is how you would do something that's sitting on an incline. Let's look at the next one. All right, let's have a look at this next one. All right, the next one, you've got 2 blocks A and B are connected by a light string and setup is shown in the diagram below. The string passes over a frictionless pulley, the coefficient of static friction and kinetic friction. So again, they're giving you that word respectively. So I know that mu s and mu, oops, what am I doing? That. I know that mu s and I know mu k. Mu s is 0.40 and mu k is 0.28. So can you see how the first word goes with the first value, the second word goes with the second value? That's because of the word respectively. When the system of the masses is released, block A slides across the table. So if it's going to slide, it's going to slide, right? Define frictional force. I'm not going to go into the theory parts. I'm only going to go with the calculations, because theory you've got to learn. For example, for frictional force, I don't want to see opposes motion. I want to see the force that opposes the motion of an object and acts parallel to the surface of the object that it's in contact with. So make sure you write a proper definition, because if I'm going to give you 2 marks, I need to give you 2 marks for something that you've actually done. Please don't just say opposes motion. Right, it then says calculate the maximum force of static friction acting on block A. All right, so if I'm looking at maximum friction for static, I'm looking for force of friction static, and the formula for that is mu s times Fn. All right, so once I've got my formula, then I can say it's 0.4, let's look at the line above, 0.4 multiplied by Fn. Now, because it's on a flat surface, I know that I've got mg there. I know that I've got up here Fn, and I know over here I've got Ft. For this one, I've got here mg going down, and then going up here I have ft. So if you can see that. Okay. All right, so Fn here would be equal to mg, right? So Fn is, oops, I'll just put this here, mg. Whatever my mg value is, my Fn value. So my mg value is 3 times 9.8. So I'll pop that into my calculator and I'm going to get 11.76 newtons. And that's the maximum amount of static friction. So 1, 2 marks there. 1.2, 1.3. Calculate the force of kinetic friction acting on the 3 kilogram block. So now they want kinetic friction. So Fk, force of friction kinetic. So that's mu k. Can you see my formulas are not the same? If they're asking for kinetic friction, you have to use the right thing. If you don't use the mu k, then I can't mark your question. So please make sure you're very careful about that one. Right, with this one, it's the same. The Fn is also the mg. So the mu value here is 0.28. And the m value is still 3 times 9.8. And that's going to give me, pop that into my calculator. Obviously, the value must be less than, I'm going to get 8.23 newtons. Now, let's have a look here. Can you see here for static friction? Static means no moving, yes? And kinetic is moving. So look at the difference in these two values. Because the higher the mu value, the coefficient of friction, the less it's going to move. So if the mu increases, then it's not going to move. So don't forget that the force of friction of static, oops, write that properly. The frictional force for static must always be greater than the frictional force for kinetic. And if your answers don't look like that, then you've done something wrong. Right, number 1.4. It says draw a fully labeled diagram for each block. Right, so we already did a little bit of a situation here, so let's just sort it out. If I'm looking at the 3 kilogram block, it's on the surface, it's being pulled by tension, and now we know that this surface has friction, so I'm going to have a force that goes in the opposite direction there. So I'm just going to draw this in here. Oops. Right, so I've got my little dot here. I know going in the forward direction over here, I've got force of tension, but pulling it back a little bit, I've got force of friction. So here I've got Ft, and here I've got force of friction. Because it's on a surface, I also know that I must have a force of the normal going upwards, and because it has mass, I must have mg. So I've got Fn there, and I've got mg down here. So that's the 3 kilogram block. And then for the 2 kilogram block, when I'm looking at it, the only thing it has here is, because of its mass, it has a downward gravitational force, and what's pulling it upwards is that tension again. All right, so I've got one force here and one force here. So over here, oops, undo that. Just get rid of this ruler. Over here, I've got force of tension, and over here, I've got mg. And that's, or I can even write weight. I can even write fg. So don't forget, you have other options. If you forget, make sure you put all of your vector signs where they need to go. And you've got yourself two sort of situations. Here, notice there's no friction. There's no friction because there's no surface. So you don't have to really worry about that. All right, number 1.5. Number 1.5 says, State Newton's second law. So you should know Newton's second law, that when a net force is applied to an object of a certain mass, it will accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass. So you must start with Newton's second law states that when a net force is applied to an object of mass, it accelerates in the direction of that net force, 1 mark. The acceleration is directly proportional to the net force, 1 mark, and inversely proportional to the mass, another mark. And look there. That's how you score 3 marks. Please don't just write there, acceleration is directly proportional to the net force and inversely proportional to the mass. It will be marked as incorrect because that means it's an incomplete law. Alright, so that's done. Number 1.6. They want the acceleration of the system and the magnitude of the tension in the string. All right, so let's have a look here. When we're looking at this system, anything that does this would be considered acceleration positive. So that means for block 1, if it moves to the right, then everything is positive. For block 2, anything that moves down is considered positive. So that's the first thing that you need to actually write down, because from there we can do calculations and so on. Right, let's look at the first one here. And the reason for that is because I know a little bit more information, right? Well, technically for both, I'm missing some information. So for example, I know frictional forces, but I don't know this tension. That's my major problem here. So let's write down what I know. So for the 3 kilogram block, what do I know? I know that the force of friction, if this thing is accelerating, it's moving. So the formula that I'm going to use, or the value I'm going to have to use for friction, for force of friction, is the kinetic friction, because there is movement, which is 8.23 newtons. My mass is 3 kilograms. My acceleration, I don't know. And the tension, I don't know. For the 2 kilogram block, there's no friction. The mass I know is 2 kilograms. The acceleration we don't know. And the tension that it's attached to, I don't know. So can you see here? I have 2 unknowns. Now the minute I have 2 unknowns, I have to solve this simultaneously. Right, before I solve anything simultaneously, let me just get some equations ready. So remember, if I need 𝐹net, I must say anything forward minus backward. All right, so let's first decide for this 3 kilogram block over here. So this 3 kilogram block, in terms of something that's pulling it forward, what's pulling it forward is the tension force. So it's tension minus, or plus rather, minus friction. So that's what the 𝐹net is for this one. The 𝐹net for the other one, so that's that one's 𝐹net. This one's 𝐹net is, what's pulling it down is the weight, and down would be positive, plus minus the tension. So there's my 2 𝐹net values for both equations. So I'm going to say 𝐹net is equal to MA. For this one, it's going to be tension minus friction is equal to mass times acceleration. So I'm going to put in what I do know. I'm going to say tension minus 8.23 is equal to the mass, which is 3 times the acceleration, which I don't know. So now I'm left with an equation where tension is equal to 3A plus 8.23. All right. The other equation, 𝐹net is equal to MA. This one is weight minus tension is equal to mass times acceleration. The weight for this one, I know is, so I must take mass times acceleration. W is equal to mg, which is 2 times 9.8, which is going to give me 19.6 newtons. So I'm going to say 19.6 newtons is minus tension is equal to 2 times A. So now I've got tension for this one is equal to 19.6 minus 2a. So I just multiplied everything by -1 to get that type of value. But I know that the force of the tension on block 3 is equal to the force of the tension on block 2 because it's the same string. So what I can do to do these two equations, I've got equation number 1 here, and I've got equation number 2, and I know that these two tension values have to be equal, so I can equate these two. So I'm going to say tension, on the 3 kilogram block, which is 3a plus 8.23, is equal to tension on the 2 kilogram block, which is 19.6 minus 2a. All right, then all I'm going to do is on this side, I'm going to have 6a is equal to 19.6 minus 8.23, which means I'm left with 6a is equal to 11.37. Divide both sides by 6, and my acceleration is then equal to 1.90 meters per second squared to the right. And if my answer obviously was negative, then I would have to change that. But that is how you would work out this type of a question. So this is the first part of the Newton's laws, the first video. And then the next video I'm gonna do is pulley on an incline, and then the 𝐹net machine. That's the last two.